Hi everybody. In previous videos I've derived and discussed the magnitude and the direction of the magnetic field due to a long straight current carrying wire. So let's just briefly recap that. So imagine I've got an infinitely long current carrying wire going infinitely in both directions. Imagine I've got a current vector going this way in the wire. If I want to find the magnetic field at some location, say right here, due to this current carrying wire, I get the magnitude of that magnetic field through this expression, where r perpendicular is the perpendicular distance, the shortest distance from the current carrying wire to this location where I want to know the magnetic field. The shortest distance has got to be perpendicular to the wire. That's why I label it r perpendicular. And I is the magnitude of the current in this current carrying wire. So I is a positive number, r perpendicular is a positive number, and B then gives me the magnitude of this magnetic field vector at this location. If I want the direction, I use one of our right-hand rules. I can use the right-hand rule in the cross product in the Biot-Savart law, or I can use a right-hand rule, one of our derived right-hand rules. Take my thumb of my right hand, stick it in the direction of the current, my fingers wrap around in the direction of the magnetic field. That wrapping sense is just to indicate the sense in which the magnetic field wraps around the current carrying wire. We know that the magnetic field due to a current carrying wire makes circles around that current carrying wire, and this right-hand rule just tells us which way those circles are going. So at this location right here that I was just talking about, stick my thumb in the direction of the current, my fingers wrap in the direction of the magnetic field. The magnetic field would point out toward you, whereas below the wire, the magnetic field would point in toward me. Behind the wire, the magnetic field would point up, and in front of the wire, the magnetic field would point down. Or I could take this current carrying wire, reorient it this way. So this little circle here is just like the outer circumference of that boundary of the current carrying wire. The current's coming this way. This little dot represents the current vector coming right out toward you. Take my right hand, stick my thumb in the direction of the current, my fingers wrap around in the direction of the magnetic field. And again, all the right-hand rule is doing is telling us which of these perpendicular directions to take. We know the magnetic field basically makes circles around the wire. To be on a circle is to be perpendicular to a radius. So if I imagine, say, this point, and this point are locations where I want to know the magnetic field. I've got these respective r perpendiculars, which are basically radii. The magnetic field needs to be in this plane and perpendicular to those radii. For each one, I've got two possibilities. So right here, the magnetic field could be this way, or it could be this way. If we only think about perpendicular, which way do I take? The right-hand rule tells me which one. So I know the magnetic field here is this way. I know the magnetic field here is this way, because that's in the sense of my fingers. I know the magnetic field here is this way, because that's indicated by the right-hand rule. I know it's not this way or that way or that way. Great. So that's our recap of the magnitude and direction of the magnetic field due to an infinitely long, straight current carrying wire. So the first point I want to make is, in doing that, we've talked about the magnitude and the direction separately. I don't yet, if you ignore this, I don't yet have that information all in one single expression. Always the magnitude and direction separately. So I want to emphasize, this is not the magnetic field vector. This is just the magnitude portion, the magnitude information, the magnitude of the magnetic field vector. The directional aspect is given by this right-hand rule. So if we want to write it all in one single expression, we need a vector expression that contains all the information. And this is that expression. So I'm just writing it here, then I'm going to discuss it, and then I want to justify it. All right, so I'm proposing that this is a fully vectorized expression that contains the magnitude and directional information of the magnetic field vector all in one shot. All right, so first let's just talk about the things that are in this expression. Looking at this portion here, that's just our magnitude for the magnetic field expression. So This I is the magnitude of the current. This R perpendicular is the perpendicular distance from the current carrying wire to the location where we want to know the magnetic field. So these symbols are the same as these symbols. All this is the same as all of this. All right, so this is familiar. Now, if this part of the expression is the magnitude of the magnetic field, then this part, which is a vector, had better be a unit vector in the direction of the magnetic field vector. That is, I can write any vector as, a vector equals the magnitude of that vector, thing without vector symbol, times a unit vector in the same direction as the original vector. Caret always represents a unit vector. All right, so what I'm saying is this should map onto this. If this is the magnitude, then this had better be, if this is going to be a correct expression, this had better be a unit vector, that is magnitude 1, and having a direction in the direction of the magnetic field vector, which should be consistent with our right-hand rule. Now, before we go and check that, let me talk about the things in the unit vector part. The unit vector has two unit vectors in it and a cross product of them. So I've got an I hat. This is a unit vector in the direction of the current. And I get I hat by taking I vector dividing by I magnitude. So I can always get the unit vector corresponding to a vector by dividing that vector by its magnitude. Or I could rearrange this and say that I vector is I magnitude times I unit vector. Great. Our perpendicular unit vector, again unit vector because of the unit vector symbol, is a unit vector that just points along our R perpendicular. So imagine I've taken this picture and transported part of it over here. So I had a current coming out of the board toward you. I've got that same current coming out of the board toward you over here. And I've just basically translated this over to here. So if I want to know the magnetic field at this location right here with this yellow dot, R perpendicular is this distance from the current carrying wire to the location where I want to know the magnetic field vector. This distance is perpendicular to the current and the wire that the current is in, so it can be the shortest distance. R perpendicular hat is just a unit vector in that direction, pointing from the current carrying wire toward the location where we want to know the magnetic field along the shortest distance. Great. So that's what R perpendicular is. Okay, so I'm proposing that this expression contains the magnitude information and the directional information correctly. So to check that, what I need to do to check that this is a correct expression is the magnitude of all of this had better be equal to that. For the magnitude of all of this to be equal to this, which is equal to this, the magnitude of this part better be equal to 1. That is, in order for the magnitude of all of this to just be equal to this, the magnitude of this portion better be equal to 1, which is consistent also with saying that this thing by itself must be a unit vector, because all unit vectors have magnitude 1. So let's check that. Let's just check the magnitude portion first. Let's check that the magnitude of this is equal to 1. So here we go. I'm going to write the magnitude of this right here, which I've done. All right. To take the magnitude of a cross product of two vectors, I need to take the magnitude of the first vector, put it here, magnitude of the second vector, put it here, and the sign of the angles between them. So I need the angle between them. All right, so let's fill this in. Magnitude of I hat is 1 because the magnitude of any unit vector is 1. Magnitude of R perpendicular hat is also 1. The magnitude of any unit vector is 1. And now we need the angle between them. Well, the current unit vector is in the direction of the current, which is along the wire. R perpendicular hat is along the direction of R perpendicular, like along R perpendicular and pointing away from the wire. R perpendicular, by definition, is perpendicular to the wire. So R hat perpendicular is also perpendicular to the wire and hence perpendicular to I hat. So these two unit vectors are perpendicular to each other. So the angle between them is 90 degrees. Sine of 90 degrees is 1. So for the magnitude of this cross product, I've got 1 times 1 times 1, which is equal to 1. So the magnitude of this is 1. All right, so this has the magnitude of a unit vector. Great. And the magnitude of this expression will be the magnitude of this expression times the magnitude of this expression. The magnitude of this expression is 1. The magnitude of this is this. So the magnitude part checks out. So let's now check the direction. I need to check that the direction of this unit vector is in the direction given by our right-hand rule recipe, which has been working for us. All right, so just transporting this picture over to here, or redoing it. If this is my R perpendicular, and this is the direction of my current coming out toward U, the magnetic field vector has got to be in this plane and perpendicular to R perpendicular in a way that is consistent with the right-hand rule. So it could either be this way or this way, and I use the right-hand rule to check which way it should be. Take my right hand, stick the thumb in the direction of the current, fingers wrap around. All right, so I know that this is the direction of the magnetic field. The perpendicular right here, there we go. Great. So that's for our right-hand rule. Now I need to check and see what direction this would give us if we work this out using our cross product recipe. So I need to use my right-hand rule for the cross product, stick my fingers in the direction of this current unit vector. That's this way out toward U. I need to curl them into the direction of the R hat unit vector. So I need to curl from here to there. And my thumb is in the direction of I cross R hat. And that's in the direction that's perpendicular to this line here. That's in the direction of the magnetic field, same direction we got by the right-hand rule. So the directional part works as well. So this expression checks out. This expression is a fully vectorized expression for the magnetic field vector produced by an infinitely long straight current carrying wire. This part contains the magnitude. This part is a unit vector that's in the direction of the magnetic field. Or if you want to do shorthand, this part represents the B magnitude. This part represents the B hat unit vector. Those two things together give us our magnetic field vector. All right, so hopefully that's interesting. If you're ever wondering, could we take our magnitude and direction, put them together in a single expression in a sort of nice, clean way? The answer is yes, we can, and here it is. All right, that's all for now. Thanks for watching, and I'll see you next time.